Welcome back to the deep dive. Today, we're going a bit deeper than usual on a topic many of you know or think you know. ADHD, attention deficit hyperactivity disorder.
That's right. We're moving past the checklist, the sort of surface level behaviors.
Yeah, exactly. We want to get into the neurobiology, what's actually happening under the hood.
Precisely. Our mission today, for you listening, is really to unpack the neurochemical blueprint. We're zoning in on two key players, norepinephrine, or NE, and dopamine, DA.
Okay. And how they control attention, impulse control, all that stuff.
And the big idea, the core insight, is about the brain's executive suite, the prefrontal cortex, the PFC. It's meant to be the conductor, right?
The CEO, yeah. Running the show. Attention, working memory, keeping behavior in check.
But here's the twist. In ADHD, it seems this area is, well, hypersensitive, extremely sensitive to its chemical environment.
And that leads to this concept you mentioned before we started, the inverted U. Sounds a bit counterintuitive.
It really is. Think of it like this. The PFC needs fuel, these chemicals called catecholamines-N and DA, but only in a very specific narrow range, like tuning an old radio.
Okay, so draw me the U. What happens?
Imagine performance is on the vertical axis, and the chemical level is horizontal. Too little chemical fuel, say when you're drowsy. You slide down the left side of the U. Your focus tanks, you're sluggish.
Right, makes sense.
But here's the key part. Too much fuel, maybe from intense stress or even too much stimulation. You slide down the right side of the U. Cognitive control weakens just as badly.
So it's not just about having enough focus juice, it's about having the perfect amount.
Exactly. That constant struggle to stay at the peak of that U, that optimal zone, that's really central to understanding the neurobiology we see in ADHD. It's about chemical balance being off.
Okay, so let's start with the stage for all this drama, the prefrontal cortex itself. We hear executive functions all the time. What does that actually mean the PFC is doing day to day?
Well, think of it as your brain's planner, filter, and supervisor. Executive functions are about coordinating everything, your thoughts, your emotions.
How does it do that?
It relies heavily on working memory. That's like your mental scratch pad, holding information online to guide what you do next. So the PFC has to sustain your attention, stop you from, constantly checking your phone.
Guilty.
Right? It inhibits those distractions. It lets you use your internal goals and plans to decide what to do right now, rather than just reacting to whatever pops up.
Okay, that sounds demanding. And our sources mentioned something interesting. Imaging studies often show people with ADHD have a slightly smaller PFC volume, particularly on the right side. Why there?
That's a really key finding, because the PFC in the right hemisphere seems especially critical for inhibition, the brain's braking system, stopping yourself from doing something impulsive.
Okay.
And look, if someone has damage, like a lesion to their PFC, maybe from an accident, the symptoms are striking. Distractibility, impulsivity, forgetfulness, terrible planning, sometimes hyperactivity.
Yeah. Wow, that's basically that ADHD checklist right there.
Exactly. It tells us this brain region is absolutely ground zero for understanding the condition.
But it's not working in isolation, is it? It's connected to other important areas. I saw mentions of the inferior temporal cortex and posterior parietal something.
Posterior parietal association cortex. Yeah, absolutely critical connections. The PFC needs good data to make good decisions, right?
Makes sense.
So it gets input from the temporal cortex that tells you what you're looking at or thinking about. And the parietal cortex tells you where things are in space, or maybe where your attention needs to be spatially. It gathers the facts.
Okay, gets the info. Then what? Sends out orders.
Kind of. It projects down to structures like the basal ganglia, particularly the striatum part. That's crucial for selecting your next thought or action, helping you stay on task.
So it stops you from just randomly switching topics.
In part, yes. And it also connects to the cerebellum. We used to think of the cerebellum as just for motor control, but now we know it's involved in cognitive stuff too, like fine-tuning thoughts, error correction for thinking.
So when people talk about the ADHD circuit, it's really this network. PFC, striatum, and cerebellum all working together, or not working optimally together.
That's the idea. That network is where a lot of the action is.
Got it. Okay, stage set. Now for the actors, those catecholamines, norepinephrine, NE, and dopamine, DA, this is where that inverted U really comes into play, right?
Absolutely. Because the release of NE and DA isn't constant. It's tied directly to how alert or stressed you are, your arousal state.
So low when you're asleep, higher when you're awake and focused.
Exactly. Moderate release when you're alert and things are, manageable. But then if something really stressful happens, think public speaking, major deadline, actual danger, The release goes way up. High arousal, high catecholamines.
And the PFC, unlike maybe older parts of the brain, just can't handle those extremes. It kind of short circuits.
That's a great way to put it, yeah. The PFC seems uniquely sensitive. Think of it like a highly tuned instrument. It needs moderate tension on the strings. Too loose, low chemicals, and you get no sound, no focus. Too tight, high chemicals, stress. And the strings snap, where the sound is just screeching noise, distorted.
So high stress, high catecholamines. It's almost like it's designed to shut down the careful planning part of the brain.
That's a leading theory. It might shift control to more automatic reflexive survival systems, less thinking, more reacting, which is great if there's a tiger, but not so great for writing a report.
Okay, let's break down these chemicals. First up, norepinephrine, NE. The sources say its good effects, the focus-boosting ones, come through a specific receptor, alpha-2A.
The A2A adrenoceptor, yes. This is where it gets really cool. Any acting here doesn't just like globally wake up the brain. It's much more specific. It acts like a signal booster.
Signal booster.
Its job is to enhance the signal relative to the noise. It literally strengthens the connections within the specific PFC networks that are doing the important work, like holding on to a piece of information for your working memory.
Okay, I saw some complex stuff in the notes about CAMP and HCN channels. Can we simplify that? What's the end result? How does it strengthen the signal?
Let's try. Think of the connections onto PFC neurons, the dendrites, as having tiny leaks. These leaks are called HCN channels. When they're open, the electrical signal representing your thought kind of fizzles out. It gets weaker.
Okay, the signal leaks away.
Right. So what A2A stimulation does when NE levels are moderate is it plugs those leaks. It closes nearby HCN channels.
So closing the leaks means the signal stays stronger, travels further.
Exactly. It increases the local resistance, so the important incoming signals have a bigger impact. It strengthens the functional connection, making the network better at holding onto that specific piece of information or goal. Better signal clarity.
That's actually a really elegant mechanism, and there's solid proof for this, right? The monkey study.
Oh yeah, it's quite dramatic. If researchers block just these 82 receptors in a monkey's PSC using a drug called yohimbine, boom, you see the full ADHD symptom profile emerge almost instantly.
Impaired working memory, more impulsive choices, even hyperactivity.
The whole package. It tells you just how critical this specific ADHD pathway is for maintaining executive control.
Which also explains why some ADHD meds like guanfacine specifically target this receptor, right? They're A2A agonists.
Correct. They're designed to optimize the function of this beneficial pathway, helping nudge the PFC back towards that optimal chemical zone on the inverted U.
But the flip side of the U, too much NE, like under major stress, that's bad news for the PFC.
Very bad news. When NE levels skyrocket, it starts hitting different receptors much harder, primarily IA1 and BAMA1 receptors.
Let's do the opposite.
Pretty much. The NE1 receptor activation in particular seems to actively suppress the kind of sustained neuronal firing the PFC needs for working memory. It basically slams the brakes on focused thought, it increases the noise, degrades the signal.
It's like turning up the static instead of boosting the signal.
Exactly. And it's no coincidence that drugs blocking the L1 receptor, like prazosin, are sometimes used for PTSD. They help reduce the cognitive disruption caused by that chronic high-stress NE state.
Okay, that covers NE boosting the signal when levels are right, killing it when levels are too high. Let's switch to dopamine, DA. If NE is about the signal, what's dopamine's main role up there in the PFC?
Dopamine, especially acting via its D1 receptor, seems to be more about decreasing the noise.
Noise reduction.
Yeah. While NE strengthens the relevant connections, DA helps to suppress the irrelevant ones. It dials down the processing of background chatter, the stuff that isn't related to your current goal. This helps to sharpen the focus, make attention more selective.
So NE turns up the volume on what matters. DA turns down the volume on what doesn't.
That's a great analogy, yeah.
Yeah.
And critically, D1 receptors also operate under that same inverted U principle.
Okay, so you need moderate D1 stimulation too. Not too little, not too much.
Absolutely. Too little D1 activity, and you can't filter distractions effectively. Too much, and you can actually become too focused, maybe overly rigid or perseverative, unable to switch tasks flexibly.
And there's a human genetics example that really highlights this delicate balance, isn't there? Something about an enzyme called COMT.
Oh, the COMT story is fascinating. Yeah. COMT is an enzyme that breaks down dopamine, specifically in the PFC. There's a common variation in the COMT gene. Some people have a version, the met allele, that makes the enzyme, well, a bit sluggish, less effective.
Meaning they naturally have more dopamine hanging around in their PFC.
Exactly. They start out with higher baseline dopamine levels. And interestingly, under normal low-stress conditions, these individuals often perform better on working memory tasks.
Because they're already closer to that optimal D1 sweet spot on the inverted U.
Precisely. They've got great noise reduction built in. And this is the crucial part, because they're already sitting near the peak.
Uh-oh. What happens under stress?
If you put them under pressure, give them a tough cognitive challenge, or even a stimulant medication, they overshoot the peak almost immediately. Their performance tanks.
Wow, so they fall off the steep right side of the U much faster.
Much faster. That optimal window is narrower for them. It shows just how sharp that inverted U can be. What's an advantage in one situation becomes a disadvantage in another.
It really underscores that it's all about optimal balance, not just more chemicals.
Definitely. And we should probably briefly mention the D4 receptor, too. There's a genetic link there with ADHD, a variant that seems to make the D4 receptor less effective.
And where does D4 fit in?
D4 receptors are found a lot on inhibitory neurons, little nerve cells that dampen activity. So if D4 isn't working well, you might get insufficient inhibition within the PFC circuits. Too much background firing, too much noise again. Another way the balance can be thrown off.
Okay, so understanding this really sensitive chemical balancing act in the PFC, the need for optimal NE via alpha-2A and optimal DA via D1, that must be the key to treatment, right?
It absolutely is. When you look at the medications that are effective for ADHD, whether it's stimulants like methylphenidate, Ritalin, or amphetamine, Adderall, or non-stimulants like atomoxetine or guanfacine.
They're all trying to do the same basic thing.
Fundamentally, yes. They all work through different mechanisms to fine-tune catecholamine levels in the PFC. The goal is to gently nudge the system back into that optimal zone, boosting the AD2A signal enhancement and the D1 noise reduction without pushing things too far.
So it's not just about flooding the brain. Like, low doses of methylphenidate seem to preferentially boost NE and DA right there in the PFC.
That seems to be the case. It's a more targeted effect at therapeutic doses, aiming for that sweet spot on the inverted U rather than just global stimulation.
Which also explains why the genetic links we see in ADHD often involve genes related to these systems, doesn't it? The dopamine receptors, the transporters, the norepinephrine system.
Exactly. The genetic vulnerabilities seem to cluster around the very pathways responsible for maintaining this delicate chemical balance in the PFC. The blueprint itself has these sensitivities.
Okay, this is fascinating. Let's bring it back to you, the listener. Maybe you don't have an ADHD diagnosis, but everyone struggles with focus sometimes, right? Especially when learning something new or under pressure.
Oh, absolutely. And this neurobiology explains why. Think about common situations that can totally mimic ADHD symptoms, just based on where you are on that inverted U curve.
Like being really tired.
Exactly. When you're sleep deprived or just exhausted, your baseline catecholamine release is probably too low. You're sliding down the left side of the U result. Poor concentration, can't sustain attention, feel mentally foggy.
Okay. And the opposite, high stress.
Right. Huge deadline looming, big presentation, relationship problems. Your stress systems are pumping out excessive catecholamines. Now you're sliding down the right side of the U result. You feel agitated, jumpy, can't settle your mind, easily distracted, maybe impulsive. Your PFC is offline due to overload.
So feeling scattered under stress isn't just in your head. It's a direct chemical consequence in your PFC.
It really is. Yeah. And this is why proper diagnosis of ADHD is so important. If someone's attention issues are mainly driven by, say, chronic stress or anxiety,
Giving them a stimulant might make things worse.
it could potentially be quite harmful, yes. If they're already way up high on the stress side of the curve, adding more catecholamine stimulation could push them further into dysfunction, increase anxiety, agitation. It highlights why you need to understand the cause of the attention problem, not just treat the symptom. You need to know if you're dealing with too little chemical signal or too much environmental overwhelm causing chemical excess.
The PFC's demand for just right chemistry forces careful thinking.
That neurochemical sweet spot is absolutely critical.
Okay, so zooming out then. If we had to boil down the core message about how our brains manage attention, what's the big takeaway?
I think it's that our highest cognitive functions, our ability to plan, focus, and control impulses, rely on this incredibly precise, moderate level of chemical signaling in the prefrontal cortex. You need norepinephrine via A2A to boost the important signal.
Making the thoughts stand out.
And you need dopamine via D1 to reduce the distracting noise.
Quieting the background chatter. It's like the brain's own advanced signal processing system.
Beautifully put, yeah. It's biochemical editing at its finest.
Okay, so for our final provocative thought, what should we leave our listeners mulling over?
Let's go back to that stress idea. Remember we said the PFC needs moderate chemicals but gets impaired by high levels.
Right, the opposite of older brain region.
Exactly. Think about the amygdala, the fear center. High stress, high catecholamines activate the amygdala. So under intense stress, these chemicals act almost like a switch. They effectively dampen down the thoughtful, planning PFC
Turning off the CEO.
and simultaneously ramp up the reactive, automatic, survival-focused amygdala. The brain shifts from deliberate control to primitive reaction mode,
Wow. So constant stress is literally chemically switching off our higher reasoning.
biasing the system away from it. So the thought to mull over is this: what's the real biological cost of living in a state of chronic stress? It's not just feeling frazzled. It might be the systematic chemical deactivation of your most advanced cognitive abilities, your executive functions. What does that cost you?
That is definitely something to think about.